Welcome to July 1st LeetCode Challenge Gray Code. An n-bit gray code sequence is a sequence of n to the n integers where every integer is in the inclusive range of 0 to 2 to the n minus 1. The first integer is always 0. An integer appears no more than once in the sequence. The binary representation of every pair of an adjacent integer differs by exactly 1 bit, and the binary representation of the first and last integers differ by exactly 1 bit. Given the integer n, return any valid n-bit gray code sequence. Alright, so if you guys didn't know, gray code is one of the versions of a binary code developed by Frank Gray, which is the ordering of binary numeral system used such that each two successive values differ by 1 bit only, one binary digit. So, for instance, if you're given a gray code sequence for n equals to 2, the bit number would be how many bit numbers you would have would be 2 to the n, would be 2 to the 2, so you have 4 binary numbers, which is 0, 0, 0, 1, 1, 1, 1, 0, which is the gray code representation, and you convert that back into digits. Alright, so let's see how I would represent this. So if you guys didn't know, I'll just give you some examples here. So if you know a bit about binary, you should be a good hand here. But if you were to write out the gray code going from 1 to 7, for example, you'd be like 0, 0, 0, 1, 1, 1. Because you see how going from top, this number 0, 0, 0 to this number, it only changes by 1 bit, which is this one right here. Going from this one to this one, the middle number only changes by 1 bit. And if you would predict what the next one is, it would be 0, 1, 0, because the last number changes by 1 bit. And then you would go down one more, which is I should probably write these out on the side here. So it'd be this is representing gray decimal 0, gray decimal 1, gray decimal 3, gray decimal 2. I mean, if you have a good strong background in gray code and binary, you should be able to do something you've learned before. And then 1 bit change would be 111, which would be gray decimal 7. And then you would go to 101, which is gray decimal 5. And then you go to 100, which would be gray decimal 4. Alright, this is the pattern for gray code going from, if you compare in decimals going down from binary, then this is the order it would go in. So this is a brief background on gray code. Oh, I have a gray code Wikipedia page. Well, so you can see that if we're given n equals to 2, we have 4 possible sets of binary numbers. So that means the 4 sets we're going to have right here are this. And going down, if we're going down the decimal index, so we go from 0 all the way to 7 using the decimal numbers, we would get the gray code binary of these numbers, which translates over to the gray code decimals of these numbers, which would be 0, 1, 3, 2, which is 0, 1, 3, 2, which is what we're returning. So that's in the most basic form. So two things to note here. Well, one thing to note is that no matter which number of n you get 2 to the n, which means that you're always returning an array or sequence where it's either 0, 1, 4, 8, so powers of 2 you're returning. So let's go over one solution here. So I'm going to think of, we can go through this iteratively. So the iterative solution. There's many ways to solve this. There's recursive, there's backtracking, but I'm just gonna go with the one that kind of first, the second thing that came to my mind actually. I'll show you why in a bit, but so the iterative way. So this one is essentially we're gonna iterate through it using two for loops, and then we'll see how I'll walk through the code here. So we're gonna develop an array to store results in. So let's call it actually output. Output would be a list. So output. So one of the good properties of Python is that the list is very similar to an array list in other languages. So it's dynamically building array. So it's great. That's a good benefit for Python. So we do output add append 0, because the first element is always 0, and as mentioned here in the conditions here, well, not conditions, but that's what grade code definition is. First integer is 0. Next thing you want to do is do a for loop. So for any element I in the range of 1, so we already have the 0 index done. So we want to range through from 1 all the way to n plus 1. Right? We want to include inclusive, right? Inclusive of the range. Now, next thing you want to do is, for looping through that, we want to update our previous length. So we're going to do previous sequence length, or prev, equal to length of output. And then, so we're going to do a fancy trick here. It's called a bit mask. So bit masking is using an Xor function. So if you're familiar with that type of logic, then you should be able to get it. So if you XOR anything, so if you're familiar with Xor functions, you know that I'm just gonna write out the function first and describe it afterwards. So it's gonna be a bit mask of between XOR 1 with I plus I minus 1. So an XOR function basically means if you have 0 and 0, 0 or XOR 0, then the result is 0. If you have, so if I have 1 here XOR with I minus 1, that means if this was equal to 0, then the mask would be 1. If this entire right side here would be a 1, XOR with 1, this would be a 0. So we want that function to be possible because due to the algebraic expression of a grade code, that's how we're going to do it iteratively. Yeah. There's a lot of, I guess, bitwise type of knowledge you need to know beforehand in order to kind of be comfortable doing this, at least as fast as I am, at least. So and we'll do another for loop in it for j in range of the previous sequence output minus 1. We want to go all the way. Okay, so range starts stop at I minus 1 index, which is all the way to n, which is the last point, and we want to traverse to this range in reverse order, so minus 1 as well. And then what we're gonna do is update our output to our list. So it'll be append. Now what do you want to append? We want to append the solution afterwards. So it would be the mask plus the results, the output I should say, at index j. And then we want to, at the end of this, return output. So yeah, let's see if this works. Looks the same. So yeah, this is using an iterative approach. So time complexity be you have two for loops, two nested for loops here, a nested for loop I should say. So it'd be big O of n to the square. Well, actually, yeah, be big O to the n, 2 to the n, because it's an iterative algorithm where we're building the list in a deterministic and non-redundant way. So that means that there's no backtracking that's occurring. So each iteration produces a series of elements or candidate elements that are part of the final sequence. So since the number of the final sequence is 2 to the n, we'll take a total of 2 to the n steps to produce the sequence. Unfortunately, I mean, that is good thing the n is only 2 to the 16. I mean, n is to 16, so 2 to 16 is still a large number though, but that's why it took a bit while. If you want to be more careful on that, more clear on that, so if the outer loop here is I, which is equal, if it's equal to 1, yeah, it would take I step to get to the output. So it'd be and then we would go through the second for loop as well. Space complexity, it's a big O of constant space, because the output is being stored. It's not is the only thing we're storing is in the output, which is an array that's constant time. That's pretty much it. So that's it for this iterative approach. However, I'll show you a kind of a neat little thing here. So during my introduction to computers class, or wherever it was where we learned about gray code, I learned this little function here where it's converting from gray code. So this is like a C code of it. So it's using bit masking as well, but this is just a little preview to it. So here's how I'm going to do it. So it's kind of neat. So instead of putting it in a list, I'm going to put it into a deck. So from it's the same approach as before, but a little bit more neater and concise. This looks better. Range of I, which is bit masked by n. I mean XOR with n, I should say. So you want to output dot append. So you want to append. This is if you know this conversion here, I'm going to use this exactly right here. Return this number right here, which is basically I to the power, not to the power, caret I one. And then you would want to return output. Right. For I, oh, in range. Finished. Looks the same as, well, no, it looks a bit weird. Yes, this should be 1. It's the bit mask shift with 1. Alright, submit that. Alright, so this solution is actually it's an iterative approach with a single loop. It looks neater because it's done in 3 lines, but however, it's 4 lines just to say. It takes a lot of like background knowledge about bitwise masking and this Xor function. So it's a shiftwise right operator, so it's an exclusive OR. So we want to it requires this is my first approach or first thought when doing this, because I already knew about the solution before, but it's just something I thought I should show you guys. It's not really easiest to interpolate to understand, but or explain at the moment, but this is it. Well, that's it. Well, in terms of time complexity and space complexity, time complexity is still 2 to the n as well, because we use a single for loop, which adds 2 to the n numbers with grade code sequence to output. Thus, time complexity is big O of 2n to the n, I should say, and space complexity is still big O of constant space because we store everything in output, which is a deck, which is constant space. All right, have a great day.